All right. So welcome to our AWS Radius Spack tutorial. This is the same as the one that we give at conferences and other venues. It's nice to see so many of you here. I'm just going to give a shout out to the whole tutorial series. So this is actually the second one of these tutorials. We're doing a bunch of these for different Livermore open source tools. And so BLT already happened. That's a build tool. Spack is this one that you're in. So thanks for joining. And then I'm sure you've seen all these others. Be sure to go check those out. MPEM's a finite element tool. There's a whole session on performance analysis tools, performance portability with Raja and Umpire. There's in-situ viz and analysis with Ascent. Axum is kind of the core framework that we use for managing simulation code data. And then I guess Weave is a workflow suite of workflow tools, and Flux is our next gen HPC scheduler. So be sure to check all those out. Today, there's four of us. All of us are Spack developers who are given the tutorial. So Greg Becker's from Lawrence Livermore. I'm from Lawrence Livermore. Tammy's from Lawrence Livermore, and Rasharda is also from Lawrence Livermore. Usually when we give this at conferences, we'll have somebody from another venue, but today you get the Livermore team. So, all right. So for this tutorial, it's interactive in the sense that we do some slides and presentations, but we also have hands-on parts. And all the hands-on demos are at this site. You can go to spacktutorial.rtfd.io. It looks like this, and it has a link back to the main Spack documentation, but it also has all the different sections of the tutorial in it. So if you get lost, or if you want instructions that maybe you missed, you can go to these sections and they have exactly what we're doing in the session in them. So you can either catch up or you can sort of focus on some part of the tutorial that we've already passed by. We're also using this tutorial channel on Slack. So if you want to ask questions, you can do that in the WebEx chat. We'll be monitoring that, but it's actually easier for us to answer over in Slack. So feel free to go over there to slack.spack.io, make an account, and join the tutorial channel there. And that way, the folks who aren't giving the presentation at any given time can answer your questions out of band in a thread in that Slack channel. This is also useful after the tutorial, because if you need help with Spack later, then there's like 2,400 people on Spack Slack who are answering questions and helping people out. So you can ask questions there even when we're not doing the tutorial. So I encourage you to go join that. All right. The other link you'll need to know, and we'll show this again before the first hands-on session, is go to bit.ly/spack-radius23. This is a spreadsheet where you can claim a virtual machine. And the way it works is we're going to put IP addresses in in column A here, and then over here the other columns have usernames, this is basically your login and your password. You can SSH to this IP with this login and password. So you would SSH 3.73.129.196 with the username Spack1, and you'd enter the password Spack1 if you put your name here. And if you put your name here in Spack2, then you're Spack2 for the same machine. The machines are pretty big, so we have up to 10 accounts on each of them. So if you want to, I don't know, come up with an allocation strategy for the spreadsheet, probably the best thing to do is to find an empty row. And if you can't do that, then find a row with not that many people in it. And then we'll keep the machines nice and balanced. At the moment, I don't think there are IPs there because Greg is still setting up the instances. So now you've seen this, you can either monitor the page or we'll show it again before the first hands-on session. Okay.
It'll be done.
Yeah, so you can get started.
Minutes.
Yeah, so if you want to grab one, go there and put your name in a box. Please do not overwrite other people's names, or try not to. This is the best we've done for allocation strategies so far. One day we will have a little web app to do this, but today is not that day. So avoid conflicts. You get one cell. So thanks. Okay. So this is the agenda. Today, we're focusing on sort of basic usage stuff. I'm going to do this intro to Spack, and then there's a basic section that Rasharda is going to do. I'm going to talk about the core concepts of Spack after you've seen it in action a little bit. And then we're going to take a 30-minute break at 9:30 Pacific. So that's in an hour and 30 minutes from now. We're going to come back at 10 a.m. for environments, which Tammy's going to do, and then Greg is going to go through configuration. And it will end. And tomorrow we're going to cover some more advanced topics. So tomorrow there's software stacks, so how to set up combinatorial software stacks, how to do a little bit of module configuration for them, how to make your own packages, and how to do scripting with Spack. And then we've got developer workflows and mirrors and build caches, basically how to set up your own mirrors and binary caches in the afternoon. Or sorry, not afternoon, in the second half of tomorrow morning, or whatever time it is for you, second half of tomorrow. So that's the schedule. Hope to see you in both parts. All right. So with that, I'm going to get started. The motivation for this tool, Spack, is that we build codes from hundreds of small complex pieces. And there's a paper written back in 2003 called Why Johnny Can't Build. It said, just when we're starting to solve the problem of how to create software using reusable parts, it founders on the nuts and bolts problems outside software itself. And so this whole paper is about why building is such a pain and why integrating code is such a pain. And this is not something new. It dates back to the 60s. McElroy was kind of the first person to do this with his mass-produced software components report from the NATO conference in 1968. And he was arguing that all these defense organizations shouldn't be rewriting the same code over and over again. They should be sharing components. And that caught on, and the pros are pretty well known. Teams can reuse each other's work. They can write less code. They can reuse software and meet deliverables faster. But you also have to make sure that all the components work together. And that means picking the right versions of everything, ensuring that everything is compatible, avoiding bugs that come from integrating software, and vetting all the components. And so this is becoming much more complicated as programs come to have hundreds of packages in their builds. And there are nasty things that can happen. You can get a build time incompatibility where things fail fast because they just don't fit, or something can just appear to work but not be quite right and fail at runtime. So there's a lot of good reasons to make sure that you have a robust integration process so that you can catch bugs like this and isolate them and figure out why they happened. Modern scientific software has lots of components. So this is MFEM, the tutorial. That's the next one of the tutorials in our series. It is a tiny little project compared to all of its dependencies. It's actually, it's thousands of lines of code. Each of these other packages that MFEM depends on is thousands of lines of code, and you have to build them all to build MFEM. Machine learning codes are even bigger than that. So LBAN is Livermore's ML training library. We also use things like PyTorch and TensorFlow. They're actually about the same size as this, like 70-ish dependencies. And then there's ridiculously complex things like the R ecosystem, where one R package might depend on 179 different things, which includes like all the things that you need to build R. So here's R condop. These are all the R dependencies up here. This is R itself, and these are all the things that R depends on. And some of the packages up here also depend on those. So it gets pretty complicated. There's even more complicated things. So under the US Exascale project, we are using Spack to integrate something that we call E4S, which is the extreme scale scientific software stack. The red parts of this graph, if you can even see that, are the sort of 100 or so core packages of E4S. They're the ones that you would say are in E4S if somebody asked you if some package was in it. The other things are all the dependencies that you need to build those packages, and together it's around 600 things. So you really don't want to build all of this manually. You need a tool to be able to work with software at this scale. Codes also increasingly leverage open source, and so even our proprietary codes like Aries leverage a lot of external open source. So this is a Livermore multiphysics code. It's used for things like inertial confinement fusion. The pink parts of this graph are packages that we develop internally at Livermore, and they're either they're just private or internal to the lab. They don't come outside, but we also have a bunch of packages that we develop externally as open source, and that's these orange ones. And then there's just external open source that other people develop that we rely on, and there's tons of those. There's 71 packages. So the bulk of this code, even though it's a proprietary code, is sitting on top of a vast amount of open source. And managing the code over time means managing all the versions of the packages, managing when you need to bump a version of something, making sure that it integrates with all the other packages in the graph, and it gets complicated. So hopefully you believe that. Traditional package managers have some pretty common assumptions that are good for distributing software to a wide audience, but that maybe don't make sense for HPC. So one of them is that there's a one-to-one relationship between source codes and binaries. Things like APT, there's a canonical recipe for each package that goes into like the Debian repo, and they build it one way so that it's reproducible. That's good for knowing that a particular binary came from a particular source. It's not that great for performance optimization. They also build these binaries to be as portable as possible, so they don't take advantage of the instructions on chips like your more advanced Intel chips that have AVX512 or vector instructions on ARM chips. They don't really optimize for the particular microarchitecture, and so you're throwing a lot of performance on the floor, especially for numerical code, if you use plain old portable binaries. And then the other assumption that is made by most of the system package managers is that there's one tool chain. And so, in a standard Linux distribution, most everything is built with GCC. And that's good, but that might not be the best compiler for the code. There's a lot of other compilers that can optimize things better. And so, Spack is really a build level package manager that's designed to address these problems so that you could use your fancy compilers. So HPC violates a lot of these assumptions. We distribute code as source. We don't really distribute code as binaries, or at least we haven't until we had optimized binaries in Spack. You often build lots of different variants of the same packages, maybe with different flags, with different build options. The code gets optimized for the processor and the GPU. So you really do care about GPU software and making that deployable in different places. And we also rely heavily on system packages. So it's not like a pure ecosystem of its own. You typically want to bring in, say, the system MPI or the system GPU library so that you're actually leveraging the hardware, the fast network hardware, the fast GPU on the system that you are working on. And then to make things even more complicated, HPC code tends to be multi-language. So there's a lot of these multi-physics codes or scientific codes are using C, C++, Fortran, Python all together. We've got codes that are using Lua. It's a very integrated ecosystem. There really isn't, one single language that people write HPC codes in. So containers are people often ask us, what about containers? Why can't containers solve this problem? And they are a great way to reproduce and distribute a software stack that you've already built. But somebody has to build the container. You need a flexible way to do that. And with HPC machines, you may not want to run the same container for reasons I outlined before across different machines. You don't necessarily want a portable container. You want one that's optimized for the particular machine. And so to do that, you really want a description of the software you're going to build in the container that is easy to change so that you can adapt it for different platforms. And so really, Spack is a more flexible thing to build containers. It's not a replacement for containers. You can totally use them together, and a lot of people really like to do that. It's a faster way to build containers and a better way to adapt containers to different operating systems. So keep that in mind. All right, so Spack's what we're going to be talking about today. It's a package manager. It automates the build and installation of scientific software, and we're trying to have it enable software distribution for HPC. To do that and to address the problems that I talked about on the previous slides, packages are parameterized so that you can easily tweak and tune the configuration. And so we tried to make it easy to install, so you could just clone it from GitHub and you can use it right out of the box. And there are these, there's a syntax in Spack, we call it the spec syntax, that lets you customize installations. And Richard is going to talk a lot more about that in the basics section. What we're trying for is the ease of use of mainstream tools with the flexibility needed for HPC. So we want to make it easy to just say Spack install HDF5 if that's all you want to do. But we also want to be able to give you control over the build if you need to do something special. And so that's what this tutorial is about, is how to use Spack and how to get it to do all that. In addition to all that, Spack can generate modules. You don't have to use modules with Spack, but you can, and you can generate modules for, say, your users on your HPC system to leverage. You can make Conda and virtual env-like environments, and there's a bunch of workflows built on top of that for things like CI and generating containers and so on. So we're going to learn about all that. If you are wondering what a package manager is, at least for the purposes of this tutorial, I sort of divide my build tools into 3 levels, where you've got a low-level build system like Make or Ninja that handles dependencies among, say, commands in a single build. If you have to build this O file first and build this O file second and combine them both to make a library, that's sort of the level at which Make and Ninja handle things, is interfile dependencies. High-level build systems like CMake and AutoTools handle they really came out of the need to handle things like library abstractions that differ by OS. And so they handle a lot of the lower level details of building targets like executables on libraries that differ between different platforms. And so they also have sort of a higher level language than Make. You say like, here's a target, it has these sources, and then the build system handles all the details of putting that together into a library for you without you having to do much about the dependencies. And then these bottom two things tend to be built for a single project. And so there might be some people working on the same code in the same repo, and it has a build system. It's typically consistent at that level. Outside of that, though, we have to integrate all these pieces of software, and a package manager is really the tool for doing that. And so the package manager drives the build. It runs CMake or AutoTools or Maker Ninja on the different packages. It fetches the packages. It runs their build system. It ensures that they're all built together in a consistent way, so you can put them together into the program that you want to build. And so think of the package manager as really like, it's like an orchestrator for integrating software. It's putting all of these disparate builds together that are built by different groups in different places and allowing you to integrate them into one piece of software. Spack's targeted at a lot of different groups. We're trying to really hit everyone across the HPC ecosystem. So that includes people who just want to use software. So if you just want to install something on a machine and run it, Spack is for you. If you manage a stack of dependencies like some of the ones that I showed earlier, Spack simplifies that task. If you just want to get your software out there for someone else to use, then Spack is definitely for you, because we would like you to configure your package to it so that other people can build it. And then finally, if you deploy software for a lot of people, then Spack can simplify that process. So user support teams at HPC centers. We've got a lot of contributors to the project, and really none of this would be possible without that. You can't really integrate like 7,000 software packages without having a lot of people working on the project. And so this is showing all the people who hit our docs site. And so I think it's it's around 7,000 monthly active users at this point. And over here, this is showing lines of code contributed to Spack over time. You can see that when we started, there weren't that many, and Livermore was sort of the first. We made the tool back in 2013. This top blue line is the lines of codes contributed by Livermore itself, and at this point, that is well under 10% of the total number of the total lines of code in packages in Spack. So this is the recipes for actually telling Spack how to build software. All these other organizations contributed, the vast majority of the code in the Spack package repo, and so the way this works is that the community works on the software. We would not be able to maintain this ecosystem without all these other community contributors. So Spack's used in the Exascale project. It's the most dependent upon thing in ECP because it integrates the software. It's not the most critical dependency because you could build it by hand, I suppose, but it does keep all of the things in ECP integrated together. It is pretty busy out there on the Spack repo. There are a lot of pull requests that get contributed. So if you want to submit your software to Spack after this tutorial, then please feel free to. We merge 400 to 600 pull requests a month. And we're getting contributions not just from sort of end users at academic institutions, but also from industry. So AWS helps us with our CI. They put a lot of credits into that. We do these tutorials, and we've gotten 125 plus people at these in the past. Google's using Spack in their HPC Toolkit cluster product. They just announced a build cache for that last week. AMD is helping to maintain the ROCm stack in Spack. HPE is they have an internal CI that tests tests a bunch of open source packages to make sure that they build on CrayPE. And actually, recently, Cray has allowed us to redistribute binaries built on top of the PE. So you'll be seeing that show up in the build cache sometime soon. And other companies maintain their tools as well. The latest release of Spack is 0.20. I'm not going to go into the details of this version, but we are doing these releases about twice a year, and each one has quite a few major features that are bundled with it. So you can check those out here on GitHub at the release notes. And this isn't the only tool that automates HPC builds. There are others, and so I just want to give you an overview of these so that you can check them out. There are these so-called functional package managers like Nix and Geeks. And actually, Spack is inspired a lot by Nix. We liked the way that Nix allows you to do lots of different software installations by sort of hashing the installation directory. You'll see how that works later. And so, and we like the way that Nix manages rebuilds of packages by using hashes. The interface of Spack is sort of inspired by Homebrew, which a long time ago was a build from source package manager. Now it's mostly a binary package manager. And there are other systems like MacPorts and Gentoo. Gentoo is probably the oldest one that can build packages from source. And what that means is that you're literally fetching the source and building the package. You're not fetching a binary to install things. Other tools in the HPC space are EasyBuild. That's probably the most direct competitor to Spack. You can check it out there. It's from the folks at University of Ghent. It's mostly an installation tool. It doesn't have quite as many of the management features that Spack has. And it's sort of focused more on HPC system administrators than Spack. We're trying to target all these different users. But check it out if you are looking for a comparison. And then finally, the other tool that comes up a lot is Conda, and its sort of faster cousin Mamba, which is really popular for analytics and machine learning data science. Conda is a binary package manager. They distribute portable binaries like a lot of the system package managers. And it's popular for data science, but it has integration problems with HPC. So it can be very hard to get Conda working with like your system MPI or with all the local dependencies that you need. So check those out. And that's it for the basics or the intro. Any questions on that before we move on to the hands-on session, or I guess, or are all the questions handled in chat? Okay, I'm guessing no. All right, so I'm going to put this up again. Greg should have the VMs up in the spreadsheet now, and yep, go ahead.
Sorry, I was on mute. There is a question in the chat about whether we have a specific page documentation using Spack on LC machines.
We don't have a specific, well, I don't know. Greg, do you want to answer that? We don't have a specific page on using Spack on LC machines now.
We have had one at times in the past, but what we have had in the past is hopelessly outdated and I think we've taken it down at this point. It could be worth doing it again.
And do we want to reiterate that we encourage people to be on Slack?
Yeah, we do. So, I mean, we are constantly available on Slack for help and on Teams internally and other places.
And there's also the join the tutorial channel on Slack. So we would like to encourage people to ask the questions in that channel and not in the chat on the WebEx, not the WebEx chat, but the Slack channel, please.
Okay. All right. I'm going to put this up again. So if you want, you should get a VM instance because this is where we're going to do tutorials. We're using these because they have a local binary cache of all the packages that we're going to install. And so it's going to be way faster if you do the tutorial in the VM instances than if you try to do it yourself on your machine. And so this is basically just to accelerate things. So go there, get a VM. I guess I will give everyone, let's do 3 minutes. So to do this, and then I'm going to hand it over to Risharda.
So I'm not able to log in. I'm able to ping the machine, so I don't think I have any like VPN issues. But I'm not able to log in with the username and password.
Okay, can you? Are you in the Slack channel? We can help you there.
Yeah, I can do that. Just gotta open it up.
Yeah, awesome. Okay, it looks like people are getting registered over there. Any other questions while we're waiting?
I'm sorry, I feel like I'm asking a dumb question here, but I registered late, and so I'm not in a Slack channel for the tutorials, but I am in the Spack channel, and I don't see anything for tutorial in the Spack.
Are you on
Slack
are you
channel.
on the Radius Slack, or are you on Spack Slack?
No,
So
I don't. I
pings-
never got invited to the Radius Slack
Oh,
because
okay.
I registered late.
Yeah, just in the tutorial channel on Spack Slack. So I guess I can just go over here. Let's see. If I can find this one. Right here.
Oh, okay.
Yeah, this channel right
this
here.
is user error. I'm not seeing all of those channels, so I think that might be the issue.
If you hit Command K, you can type the name of the channel and go to it
Okay.
like that. And
All right. So just
the other way to do
tutorial
that
or
is
ISB
yeah.
23. Which one?
Tutorial. Yeah, just tutorial.
Okay. Great. Thanks.
Okay. All right. So with that, I am going to hand it over to Risharda so she can get started on the basic section. All right. So I'm stopping sharing. If folks still need help with VMs, then ping us in either WebEx chat or in the tutorial channel on Spack Slack. And yep, take it away, Risharda.
All right, I will be covering the basics of Spack here. Let me share my screen. There we go. Can everyone see that?
I can see that.
Great, off to a great start then. All right, so this is the Spack tutorial landing screen, and we're going to scroll down and cover the basic installation tutorial. So this will cover installing, uninstalling, and finding installed packages, as well as the basics of customizing the installations on the command line. So Spack is designed to work right out of the box. So we'll just git clone Spack and start running. Use this line here. So I'll type it in over here. That's equals 100. And we're gonna check out the branch release of version 0.20. And everything we're gonna do today would work at the tip of the develop branch, but just to make things simpler, and we're just gonna check out the most recent release. So we have stable dependency resolutions. GitHub. Git Spack. So now we'll look to cloning Spack. And we will cd into our Spack directory. All right, so all we need to do now is add Spack to our path, and then we're good to go. So Spack has this cool command line integration. So instead of appending it to our path variable, we will just source the setup script. .share /Spack /setup -env.sh. Now, if you run which Spack, we should see it, our path to it here. Now we're all good to go. And I'm just going to take a quick pause to make sure everyone has caught up to this part, because this is very important. Make sure we don't miss a step with this. And if you're having trouble, be sure to just go back through the instructions or get on Slack and ask for help there. All right, once everyone's got this, we're going to check the packages that Spack has available by running Spack list. So once this gets through, we're going to see over 7,000 packages just run past us really quickly. But the first time getting all those packages, it's going to be kind of slow. there's a lot of information in the package files that Spack needs to be able to do the dependency resolutions. So the first time we were going to build up some indices to be able to do things faster. So after that, when we run Spack list the next time, it'll be almost instantaneous. Getting all those 7,000 packages is going to take a little bit the first time. There we go. Got the 7,100 packages. And if we were to run it again, see it happens just like that. But that's a lot of packages to deal with. Let's try filtering them down. For example, Spack list, let's do pi-star. Now this is giving us all the Python packages Spack has available. This is a little naming convention we use for the Python packages. They're all going to start with py dash, and then it's going to be the package's name. We can get, for a more specific example, we'll try Spack list YAML. And you see for this example, I didn't put the star on anywhere. So Spack's just going to assume it's on both sides of the package name, and it's going to give us all packages that have YAML in the name. This is really useful for finding out if Spack has the package you want to install or finding what the name of the package is in Spack. But what we really want to focus on now is installing these packages. So like I said earlier, Spack works right out of the box. So let's immediately go into installing zlib. Spack install zlib. So we picked zlib as an example because it installs very quickly and virtually everything depends on it. Here comes when we have zlib installed, you'll see this hash here in the directory, and that's going to become very important later. We're going to talk about that later. So we just installed for source, and in addition to installing a package from source, Spack can also install from a binary cache, what we call a mirror. So there are a couple commands we need to execute first so that we can access these pre-built binaries for the tutorial, and we can compile things more complicated than zlib later. So let's run this first command, Spack mirror add. We're going to call it tutorial, and we already have it here in /mirror. We have we have already pre-populated this and onto the image for you in /mirror. And this could be a URL, an S3 bucket, or from a web server. But since we already have it in the file system, we're going to use that. And that way, we're not going to be so dependent on the internet. The next command we need to run is Spack build cache keys -- install -- trust. This is saying, look at all the mirrors that I've got and get me all the public keys for them, and I'm going to trust those keys. The only one we'll get here, see, we only have one processed and one important. This is the one that's created for the tutorial, and we're going to use this because it's a way for us to install things quickly. Now we got all that done. Let's get back to installing packages. So as Todd mentioned before, Spack has this spec syntax, which is how you would describe how you want a piece of software built. To specify a specific compiler, you would use the %sigil. So for this example, we're going to use clang, so Spack install zlib %clang. All right, so you can see here we have clang used to install zlib, and it has a different hash than the zlib we looked at before. This is really important. It's just making sure that we link to the exact zlib that we want. And because this could become difficult to navigate, we use our paths to install the packages so that they automatically can find their dependencies. But this will be covered more in the concept section. All right, let's say we wanted to install a different version of zlib. We don't like 1.2.13. We first need to see the versions of zlib we have available by running Spack versions. We'll do Spack versions zlib. You'll see that we have two sections. We have the safe versions and the remote versions. The safe versions are the versions of this package zlib that Spack already knows about. Someone has put them in the Spack package and we have checksums for them, and we can make sure that we're getting exactly what we want. The remote versions are versions that Spack can spider the remote server for, saying, what are versions of zlib I think I can find doing some regex replacement on the URLs I already know about. We're going to just ignore the remote versions for this since they don't have checksums, and we're going to focus on the safe versions. Let's do version 1.2.8. And the sigil to specify a version is the @ sigil. So we'll do Spack install zlib at 1.2.8. All right, now we have our zlib of 1.2.8, but the @ sigil can also be used for specifying versions for compilers. Let's try that out. Do Spack install zlib. We'll do %gcc. We're going to do version 10. You see here we'll have gcc at 10.4 with our zlib. So another thing that can go in the spec is compiler flags. And we support the standard compiler flags. We have C preprocessor flags, C flags, CXX flags, F flags, LD flags, and LD libs. Let's do an example with C flags. So we'll do Spack install zlib. We'll do @ for our version, which is 1.2.8, and C flags. It's going to equal -O, the letter, and 3. So now we have zlib with the C flag of -O3. And we put the C flags maybe because we don't know that zlib is already a pure C package, and we want to make sure it applies to all the languages. So now we have our optimized version of zlib. Now let's take a look at all that we've done so far. Using the Spack find command, we can look at all of our configurations. Spack find. So now we have 4 different configurations of zlib installed. We can get a little more information using these flags. We're going to use L and F. Spack find. We're going to do -L for long. That'll give us the beginning of the hash. And F for flags. Here's the hashes for this configuration of zlib and our flag here. If we didn't specify a flag, we're just not going to see any flags for the configuration. So this hash is the hash of the full provenance of the spec. Since zlib has no dependencies, there isn't much that goes into it, but the compiler, the build options, and all that is part of the hash. This is also how we check to see if 2 specs are the same. As we move into more complicated packages, we will see that Spack reuses the existing packages if the hash matches the desired spec. So let's move into something more complicated. We'll install Tickle. Spack install Tickle. So Tickle depends on zlib, but you can see here we didn't have to go through installing zlib again. Spack looks up the hash to see if there's already a zlib there, and it just moves on to install Tickle. Are there any questions that we should address from the Slack channel here? Just to take a pause.
No, I think you're good to keep going.
All right, great. Then we'll go on to the next part of the spec we can use, which is specifying dependencies. And for that, we're going to use the caret sigil. So let's try installing another configuration of zlib. Tickle. Spack install tickle. We do caret and specify we want zlib. And we want that version to be 1.2.8 and %plang. For this, we're going to be using a zlib configuration we haven't built before. So we have to install a new zlib with this version and using Clang. And we'll have a new tickle as well. If you look at the path, you'll see that both zlib and tickle are using Clang. Since it's using Clang for the dependencies, Spack knows that generally you probably want the compilers to be the same. If you really want to, you can be specific and tell Spack to build different parts of the spec with different compilers. But if you don't, Spack is just going to unify it under one compiler because that's most likely what you want. All right, a package can also be referred to on the command line by its hash. Let's install another tickle using the hash of a zlib we already have installed. So Spack install tickle and caret for dependency again. We're going to do slash, then the beginning of its hash, ISW. So you see I didn't put out the full hash. I just needed to give enough of the hash for it to be unique, so enough for Spack to figure out which one I meant. So here we didn't install a new zlib, but we do have a new tickle. All right, let's take a look at all that we have installed now using Spack find again. Do Spack find. We're going to do L for long again, or do D to look at the dependencies, and F for flags. Here we have our tickle with its zlib dependency, and you'll see that these two have the same hash, since these are actually just the same spec. Now let's go on to a slightly more complicated package than tickle, and we're going to do HDF5. Spack install HDF5. All right. HDF5 is a good example due to it being one of the most used packages in HPC, and it also has an MPI dependency. And you see that we are installing HDF5 with no other specifications. And since it depends on MPI, Spack is going to use OpenMPI by default, which also has a lot of dependencies, which are going through installing right now. As that goes by, you'll see that, as I said, since the MPI dependency, we're going to have OpenMPI installed and then our HDF5. Next, we're going to talk about another one of Spack's build options, what we call variants. So here we're going to talk about Boolean variants, which can be enabled with the plus sigil or disabled using the tilde or minus sigil. We allow for the tilde or minus sigil for disabling to allow flexibility in spacing. For example, if you tried Spack install HDF5 minus MPI with no space, Spack would think you're trying to install a package called HDF5-MPI. That's not what we need. So you can add a space here, and then Spack will understand that it's a variant, or you can use the tilde with no space, and we're going to go with the tilde. So this will install a new HDF5 with MPI disabled. And since we already have all these other packages installed, it's just going to quickly go through those, check for the hash, and just install a new configuration of HDF5. And there it is. Oh, it's my mouse. Okay, so let's try doing HDF5 again, but with a different configuration of MPI. We do Spack install HDF5. We're going to enable the variant HL and then make sure MPI is enabled. And for its dependency, we're going to specify MPitch. So using
Which compiler did it use by default?
OpenMPI is used by default.
The compiler, which compiler did it use?
Oh, the compiler is GCC.
Okay,
It will
thanks.
use the newest GCC that it can find on your system by default.
Okay, thank you.
No problem. So Spack has OpenMPI, MPitch, and InVapage, and more to provide the MPI interface. So here we specified MPitch, but as I said, it'll use OpenMPI as default. There's our MPitch. So let's check out what we have installed, because we've installed so much more now. Spack, find, we do L for long, D for dependency, and F for flags. And now we have 58 packages installed. We can scroll up. Let me scroll down here. You can see this. Yeah. And we'll scroll up and we'll find our HDF5 instances. You can find them. All right. Here's one HDF5 that has MPitch here. This HDF5 with OpenMPI. Now this is the HDF5 we did with MPI disabled. And you'll see that all of them have the same hash for CMake, the OFS. All right, next we're going to talk about how Spack models the dependencies. We're going to, the Spack models the dependencies of packages as a directed acyclic graph, a DAG. We're going to do an example of this with Spack graph. Do Spack graph. Let's do that HDF5 example we just installed with HL enabled, MPI enabled, and MPitch dependency. So this will show us the tree representation rather than just having them here like this. This will graph out the entire DAG. It'll look, I find it more easier to read than this. And we get pretty colors with it. So this is our DAG for our HDF5 with MPitch. So we have gone through the more complicated package of HDF5. Let's check out something even more complicated, Trilinos. So let's Spack install Trilinos. We use Trilinos as our very complicated package example because it's very useful, it's widely used, and it's very complex, which is what makes it such a great example. So Trilinos has 23 top-level dependencies, and many of them have their own dependencies. Figuring out how to install Trilinos can stop even an experienced user for weeks. Although we are using a binary installation for the tutorial, if Spack were to install Trilinos from source, it would take about 3 hours to get everything, 3 hours to get it if you did everything right. But it would only take about 20 seconds of the programmer's time. So as you saw, we installed Trilinos with no other specifications. So for the BLOS dependency, it's going to use OpenBLOS by default. And you see that we are reusing a lot of the packages we already have installed from our HDF5 dependencies. So let's try installing Trilinos with a specified HDF5 one that we already have installed. Spack install Trilinos. We're going to have HDF5 enabled. And for the dependency, we're going to say the HDF5 with HL enabled, MPI enabled, and for the dependency of that, we're going to have MPitch use. So this is the same HDF5 Spack we already have installed. So Spack isn't going to go and install that again. It's just going to reuse it. So after this, we will have 2 different configurations of Trilinos installed. While that goes, are there any new questions we should address here over WebEx?
I had a quick question. So if you have multiple dependencies and you want to specify the dependencies of the dependencies. So like your example, you have HDF5, you wanted to point to mpitch.
Mhm.
Let's say you had another package and you wanted to point to one of its dependencies. Is Spack complete enough to parse that line in a way that groups things correctly, or there's some limitations there?
No, it'll be able to parse the spec properly.
Okay, so you can be very granular about what you point to without using hashes, for example.
Right. Yeah.
Okay, cool. Thanks.
No
You
problem.
can refer directly to hashes, which I think we are going to show too.
Right.
Yes, you can do that too.
The only thing you need to keep in mind when you write options on the command line is that like the variants and versions and things associate with the package immediately to the left of them. So if you
Okay.
put like HDF5 depends on zlib, and then you start putting options there, they're on zlib, not HDF5.
Right.
You would put them before the zlib if you wanted them to associate with HDF5. That's all.
That makes sense.
All right. Great. Glad we can answer the question. So now we're going to go look at the DAG for trilinos using spec find -d. Find -d trilinos. This will give us both the trilinos installed installations. So here's our trilinos with our HDF5 and mpitch. And here is our other trilinos with the default using OpenMPI. Let's take a look at that graph for trilinos. We're going to do graph trilinos. So this will show us the full DAG of trilinos with all the dependency information, and it'll give it to us in pretty colors and all mapped out. I'm a little biased for it. So you can also get the full graph running Spack graph, but also using the --dot flag, you can have it outputted in graph viz. All right, there is our trilinos. And since we didn't give any specifications which trilinos, it gave us the one that we installed with no other specifications. Here's our OpenMPI. But now let's get into uninstalling packages. We have installed way too many configurations of zlib and tickle. Let's get rid of some. So let's check out the ones we have for tickle using Spack find. Spack find, we're going to do -d for dependencies, -d and tickle. Let's see, we have our 3 installed packages of tickle with its dependencies. Let's check out our zlibs. Spack zlib. Oh, I forgot it's fine. Spack find zlib. And we have 5 installations of zlib. So there are multiple ways to uninstall a package. You can use that same spec that you use the same spec syntax you used when installing it. So we'll do spack uninstall. I'm going to do -y, so it doesn't ask us a question. Without -y, it'll ask, do you really want to uninstall this? We'll just say -y for yes. We'll zlib, and we're going to say GCC for our compiler at 10. Now we have successfully uninstalled zlib. So if we were to run spack find on it again, spack find -l for long, f for flags, zlib. Now we only have 4 installations of zlib. Another way you can uninstall a package is by referring to the hash. So let's do spack uninstall. We're going to do zlib, and the hash is going to be fdy. Now we got this error, and this is letting us know that there's a package that is dependent on this this installation of zlib. So there's different ways to get around this. You can force it using -f, and that'll get rid of the zlib, or you can use -R. That'll get rid of the package and the dependents, or dash dependents. That'll do the same as -r. So let's try using -r for this. Spack uninstall. We're going to do -y for yes, and -r to get rid of the dependents as well. We'll do zlib 5dy. So now we have uninstalled both tickle and that zlib. Let's uninstall Trilinos. And here we can expect an error trying to uninstall with just Trilinos, because we didn't specify which Trilinos we want to get rid of. There are multiple that match this spec. So we can either be more specific with our spec, or we could do --all. It'll get rid of all instances of that package. Let's just do it with a hash. We'll use this hash here. Spack uninstall. I'm going to do /vcj. This is what it asks if you don't use the -y. So we'll say, yes, we want to proceed. Now we have successfully uninstalled our Trilinos. Next, we're going to check out additional uses for the Spack find command. We're going to go over what's called anonymous specs. These are spec constraints that don't include the package name. So we're going to do something like covering the dependencies. We'll do Spack find, and we want all the packages that are dependent on mpitch. So we have our HDF5 and our other Trilinos here. We can also do that, use this for covering flags. So for example, Spack find C flags equals -- the letter O3. We have one installation for that. Spack find can also be used to locate packages using the -p flag. And it can also be used to filter out specs to only look at the ones you specifically said to install using -x. So we'll try that. Spack find -p for location of the package and x for explicitly installed. Now we have our locations, and we're not getting swarmed by all the dependencies of Trilinos and HDF5. The last part of the basic usage section will be about customizing compilers. So everything we've built so far, we've built with compilers that Spack has just found in the system. We can use Spack, we'll run Spack compilers to take a look at those. Spack compilers. These are the ones that we've used so far. These are just ones we found. This shows the compilers that were in our path when we logged into the VMs. If we want a little more information, we can run Spack compiler info, and we'll specify the GCC at 10. This gives us, we see the paths to it, the system compilers, and the operating systems. But let's say we want to have a new and different compiler than what's on the system. We can install it. So we'll do Spack install GCC at 12. It is important to note that installing a compiler is not the only thing necessary to do to tell Spack to use it. There is a distinction currently between having something installed as a package and having it available as a compiler. So this might not persist in the future, but for now, this is an important thing to keep track of. So this is saying we're installing the package GCC at 12. So now when we have that installed, we need to tell Spack that this GCC we installed is a compiler that we can use. So next we're going to need to find the path, and we can use that during using Spack find -p like we did before. But we also have another way of finding the location. We could use Spack location -i. So these are two ways, and then we need to tell Spack to look for the compilers, and we can do that in two ways. We can add the compiler to our path, and then say, hey, Spack, go look at the path again and look for compilers. Or we can give Spack a hint saying, hey, go find compilers in this directory. So we're going to do the latter using the Spack compiler add command. Spack compiler add. We're going to tell Spack the location using Spack. Oops, need the parentheses for that. Spack location -I. We want the GCC at 12. Hey, there we go. Added one new compiler. Now Spack's found it. So Spack uses by default, as Greg said earlier, the newest version of GCC available on your system. So by adding GCC 12, we have now changed the default compiler. So next we can just try removing it. We'll do Spack compiler remove GCC at 12, and GCC has now been removed. And that is the end of the basic usage section. Are there any questions?
Yeah, I've got one. So you said that now the default compiler has been changed since we added a newest version of GCC. What does the concretizer prefer if I was to reissue a bare Spack install HDF5? Will it try to install it with GCC 12, or will it, because that's the default, or will it prefer the one that's already installed, even though it doesn't satisfy the new default compiler?
I believe it'll try to use the newest version of GCC. It'll use the 12.
Cool. Thanks.
It depends whether you have reuse set on in your concretizer config or not. If you have reuse set on, it will prefer reusing the one which is the if you have reuse set on, it will prefer the one that's installed. If you have reuse set off, it will prefer using the default compiler. The default setting for reuse is this in-between setting called reuse dependencies. So for HDF5 itself, it should prefer getting the compiler right, but if it was being pulled in as a dependency for something else, it would prefer reusing the one that was already there. Of course, unifying compilers across the DAG is also a pretty high priority. So it would depend on kind of the minutia of exactly the use case which you would see.
Okay, thanks. And as always, be explicit if I care, I would assume.
Yeah, exactly. If you're explicit about it, Spack will either do it or tell you why it can't.
All right. No more questions. This is how to stop. There we go. Oh, if there's no more questions, then I will pass it on to, I don't remember who's going
Me.
next.
Hold on. Let me get set up here. Thanks, Ricciardo. That was great.
Thank you.
Let's see. Okay, let's get back over here. Get ready to share. Okay, so Ricciardo's gone over a lot of the basic usage of Spack, so you've sort of gotten a feel for what it looks like to use the tool. This is really just these slides speak to the core concepts of Spack, so we can sort of reinforce what you saw in action, and so you understand how it works under the hood. So the real thing that differentiates Spack from other package managers is the combinatorial versioning. So you saw that essentially every package gets a hash that is made up of its configuration and all of its dependencies configuration. That enables us to install sort of arbitrary versions of things, built different ways, built with different options, and so on. Your traditional binary package managers like RPM, Yum, APT, and so on are really designed to manage a single system stack and to install one version of every package that gets upgraded over time. Spack is putting every package in its own directory. And so, when you install a new version of something, it's non-destructive. The old version stays, and you can remove it. But every version of something in Spack that has a different configuration is a different installation. Port systems like BSD ports, portage, MAC ports, and so on are similar. They're just building from source. They're also installing to a common prefix. There is a little bit of multi-versioning in Gen 2, but it uses things like tweaking the names of executables and so on within a prefix to differentiate things. So you can have like Qt5 and Qt6 installed at the same time, but you can't have you know, zlib 1.2.1 and zlib 1.2.2 installed at the same time. So virtual machines are another way to do this, and so are containers. But really, those are, they allow you to sort of reproduce different versions of an entire OS image. And here, we're really just going for multi-versions of particular packages. So it's a much finer grained thing. Well, I realized I didn't turn on my camera. How do I do that from here? I'm not seeing it. All right, I'm just going to leave it off. Okay, so you saw the spec syntax, and we got a lot of really good questions in chat about this. The spec syntax describes custom package configurations, and this is one of the sort of, I'd say, 3 core pieces of Spack. If you say Spack install MPI leaks, that says get me MPI leaks, but I don't care how it's built. Just get me a version of it that runs, and so we call that unconstrained. If you say Spack install MPI leaks at version 3.3, then that says I want that specific version. I can control that. If you want it built with a particular compiler, you use the % sigil like Richard has showed. You can put options on. So MPI leaks the package exposes different build options. So if you want threads, you can say plus threads. A lot of packages have say plus debug or other options. And those can be either plus or minus, or there are some options that sort of take string values that you can pass in. There's lots of different types of variants in Spack. You can inject flags. So you can say, hey, build this whole thing with O3G3. Or whatever other combination of flags you can do. That can be useful if you want to build an entire stack with, say, if you want to build, say, an address sanitizer version of something where you have to apply special flags to every package in a build, you can easily propagate that through with Spack. And finally, you can target specific microarchitectures. So here, this is showing that I want to build for Cascade Lake. Which says take advantage of every instruction that's available on the Cascade Lake microarchitecture. It'll pass that through the compiler, and the compiler will build with that particular target in mind. And then the syntax is recursive. Let me fix this slide really quick. I guess when I pasted that, it got a little off. There we go. All right. The last thing you can do is you can pass recursive options to your dependencies. So when you say Spack install MPI leaks at 3.3, depends on mpitch at 3.2. And you say %GCC at 493, you're saying you want that whole thing built with GCC. It's really saying, hey, Spack, make mpitch built with GCC. But Spack also tries to match the compiler between the target and its dependencies. So what practically happens is that this gets propagated up to MPI leaks. All right, so each of these is a spec for a particular configuration. All of these are constraints, and essentially you are narrowing the set of packages that you may be referring to by providing these on the command line. And it's recursive, so you can do a lot of things with that. The way that this that we enable this type of syntax on the command line is that Spack packages themselves expose a lot of options. And so if you look at the recipes, and we'll get more into this in the package creation tutorial later, every Spack recipe is a Python class. And so it looks like this. You've got, this is script-key. It's a little mini app that we have at Livermore for SN transport. It says class script-key. It extends CMake package. And so that provides a bunch of CMake support sort of out of the box. And then there are really 2 parts to this package file. The stuff up here from, say, homepage down to depends on is all metadata. And so it's telling you some things about the package. So there's like a comment up here, there's a homepage, there's a URL where you can download the package. And then there's these things called directives. And so there's a version directive there. Sorry, my mouse keeps messing up. The version directives say what versions are available. And so each of them has a checksum next to it. So it says if I download version 1.2.3, which it'll extrapolate from this URL, this is the SHA for version 1.2.3. So I can check that I downloaded what I expected using this checksum. And this is for security. You don't want to just arbitrarily download something from a URL without checking it against what the packager intended you to get. Variants are exposed with this variant directive. So basically this says there's a variant called MPI. It defaults to true if you don't specify anything else for it, or nothing else forces it to be off. There's a variant called OpenMP, which also defaults to true. And this is what enables the user to set these options on the command line. So you can say crypt key plus MPI or crypt key plus OpenMP, crypt key tilde MPI for turning it off. The variants themselves, depending on their values, can affect other things. So down here, you've got a conditional dependency. So it says I depend on MPI when MPI is enabled, right? So when plus MPI, I have this MPI dependency. And then this says I depend on CMake at version 3.0 or higher, and it's just a build dependency. I only need it at build time. So all of this stuff up here, the directives, is really specifying, you could think of it as specifying the space of builds that are possible. It gives you all the versions, all the variants, and so on. Some of them can be conditional, and that is telling you what's possible. What's the space of things that I could create, what's the space of crypt keys that I could create. Down here, what Spack is going to do with all this information is when you install something, it picks a configuration from that space. So it's going to pick a version, it's going to pick values for all the variants, it's going to pick, it's going to enable the dependencies that are needed, and it's going to pick versions for all of them. And then it runs these instance methods down here. These are basically the package recipe itself. And so here, because we extend CMake package, the install method with all the install logic is abstracted. You can write your own if you want. But what this is saying is this is how you need to configure this package with CMake. When you run CMake, pass -d enable OpenMP and set it to whether or not OpenMP is enabled in the spec. So if Spack decided that OpenMP was enabled, this will be true. If not, then it'll be false. And so you'll get -d enable OpenMP equals true or false. Same for MPI down here. And so what that's doing is it's controlling how CMake is run during the build process. Down here, this is the install method. And we've overridden the default one, which would normally just run make install because this package didn't have a make install target at the time. And so it's a good example of how you can customize the logic. So Spack will run CMake with the CMake arguments, it'll run install. And then this just makes a bin directory within the prefix where you're going to install the thing, and it copies the executable into the prefix. Really, the install method, it takes a spec, which is the configuration that Spack chose, and it takes a prefix, which is where you're supposed to put the installation, and that's it. So these build recipes are basically taking some configuration and putting them into a prefix. So that's sort of a high-level view of the packages themselves. We'll get more into creating your own packages later, and there are like 7,000 of them in the Spack repo that you can browse if you want to see how different recipes are done. We'll learn more about that later. Conditional variants are a way to, are something that we have for expressing, when packages have different options. And so we've integrated a lot of GPU support into Spack, and there's a whole lot of complexity in the GPU stack. So some packages can have CUDA enabled sometimes, and if they have CUDA enabled, they can have other options too. So like the CUDA architecture, if CUDA is enabled on the package, you also need to specify the CUDA architecture. So if you extend our CUDA support, this is just an example, you get this CUDA variant here, and it defaults to false, so CUDA is off by default. If you put plus CUDA, then you also get this CUDA arch variant. See, it says when plus CUDA. It exists only when CUDA is enabled. And you can pass it CUDA architecture values, so like 70, 72, 75, and so on. This enables us to specify a lot of cruft that you probably don't want to specify yourself. And so this is abbreviated, but if you look at the CUDA package in Spack, it has a bunch of constraints that basically say, when if the user asks for CUDA Arch 70, then I need CUDA 9 or higher. If they ask for 72, I need CUDA 9 or higher. If they ask for 75, then I need CUDA 10 or higher, because the older versions of CUDA don't support generating code for this GPU generation. Same down here, different CUDA versions on different platforms have different support for language levels in GCC or in other compilers. And so we have all of the relationships defined in the CUDA package of what compiler version do I need with what version of CUDA to support the language level that it's written for. And so none of this is stuff that you really want to think about when you're installing a package, but Spack's CUDA package support makes it so that if you do write a package with GPU support, you have all of this built-in logic that you can use to ensure that your install is consistent. And these are the types of things that really bite you when you're trying to get a large software stack integrated. So we have a bunch of checks that are defined for these packages. There's a similar package for Rockham, and really the point of this slide is that the support in Spack for conditional behavior for different types of constraints is pretty robust, and so we have you can write a lot of complex packaging logic into into packages for other people to reuse. Specs can constrain versions of dependencies. So we saw this earlier, that the syntax is recursive. So if you say Spack install MPI leaks, build it with the Intel compiler at version 12.1, and it depends on libelf at 0.812. The interesting thing about this is that you don't really have to know that much about the structure of the graph. You might be building MPI leaks and you might see that, the latest libelf version is causing me problems. And I know that the older version worked. So I can go and install just libelf at 0.812 and ensure that it's linked to MPI leaks without really knowing that MPI leaks depends on call path, depends on dynast, and that there are really two paths here by which I could get to libelf. I don't have to know all that. I can just say, hey, it's libelf, that's the problem, go give me version 0.812 and make it work. And Spack will solve for a graph that satisfies these constraints here. The other thing that we do, and you may have noticed back here in the example package, that we depended on MPI. MPI itself is not actually a package, it's an interface. And so we have what we call virtual packages in Spack. So MPI is a virtual package. MPI leaks depends on MPI, but practically when the installation is done, what really happens is that the MPI node here gets swapped out for either MVAPitch or OpenMPI or MPitch or whatever the MPI you've chosen is. So you can even conditionally choose, which dependency you use to satisfy a particular constraint. And you can, and this enables you to specify using the same syntax that we described before, what MPI implementation you want to use with a particular build. So if you have a package like MPI leaks and it depends on MPI, you can say depends on MVAPitch at 1.9. You can say depends on OpenMPI at 1.4 or higher. It doesn't matter. You use the same carrots syntax. And Spack knows that this is an MPI provider and that it can use that to satisfy this MPI dependency. Now, this is something that's usually done in the package. The packager would write depends on MPI, and then you, the user, you could provide a specific implementation. You can also write the virtual on the command line. So you could say Spack install MPI leaks depends on MPI at version 2. This just shows that the MPI version itself is versioned. And the use of this is really more inside of packages. If you have a package that needs, say, non-blocking collectives, then you could say I depend on MPI3. And Spack will ensure that when someone does this, Spack install MPI leaks with a particular MPI implementation, that you get an MPI implementation that has, that provides the MPI version that you asked for, or that it fails. But usually the package would specify this, but you can also use it on the install line. It's the same syntax. All right. So the final piece of Spack, you've seen the spec language, you've seen the package files themselves. The thing that puts them all together is what we call the concretizer. And when you get a specification like this on the command line, it says, I want to install MPI leaks with the call path library at version 1.0, with the debug option and libelf at 0.8.11. Spack has to go and fill in the blanks for all of the things that you didn't specify, right? So what it does is, it takes the graph notionally, it normalizes it, it sort of generates empty nodes for all the things that you didn't mention. It puts the constraints that you did mention on the nodes where they matter. So here for MPI leaks, you depend on call path at 1.0 plus debug. This is libelf at 0.8.11. And then it fills in all the blanks for all of the nodes there and gives you what we call a concrete spec. So this is abstract up here. Abstract because it could refer to lots of different installations. And a concrete spec basically refers to a single installation. It's one that's fully specified that you can actually go and build. That gets stored in a YAML file, actually it's JSON these days, in Spack's database of packages, which is what you're querying when you run Spack find. And so we save all this provenance from the different packages so that you can go and query it later. And then that's also what gets passed to the package recipe that says, here, this is what you're supposed to build. And it's the packager's job to basically say, okay, if I'm supposed to build something with this particular compiler, if there's anything special I have to do for that compiler, the logic needs to get encoded in the package file, and so on. So essentially, if you're thinking about Spack, there's three pieces: the spec language, the package files, and then the concretizer that ties the two together. The user specifies the constraints in the spec language. The packages have some constraints in the spec language as well that say what's possible. And then finally, the concretizer sort of tries to pick the best configuration for all that and gives you one concrete thing. So that's what's happening when you use the tool. Hashing is how we handle all this complexity. So when you get a concrete spec with everything filled in, like in this graph, the entire graph with all of the configuration options that Spack picked is hashed. And so you end up with these installation directories that have hashes in their name. That ensures that we can get you a unique installation directory for every configuration you can think of. That can be a little messy when you look at it, but one thing that we do to ensure that your library can still find all of its dependencies is we embed something called rpaths in binaries. And if you're familiar with LD library path, that's an environment variable that you set that says, hey, look here for your dependencies. Spack basically makes every library know where its dependencies live. So, this version of Python here will know where its bzip2 lives and where its SQLite lives and so on. It basically has pointers out to these other directories so that you don't have to mess with LD library path to get things working. And the idea there is that when you built the package, or when someone wrote a recipe for the package, they knew what they were doing. They knew what all the dependencies ought to be. When you get around to running it, you may have forgotten. You probably don't remember the 100 packages that you had to build at build time, or you may not even be the person who installed the application. And so we want the binaries to remember what they were built with so that it's easy on the user. They can just run it straight out of the directory. All right. Okay. The other thing that Spack does for you is it has this isolated compilation environment that lets you easily swap compilers. And so inside the compilation environment, we set a bunch of environment variables that essentially control the behavior of some wrappers around the compilers. And the compiler wrappers themselves are adding things like include directories and library directories and rpath arguments for all your dependencies that basically ensure that you are linking against the right things. We try to make it really hard for you to point at something that is not one of your dependencies. And we try to make it so that you don't have to do a lot of work to get these rpaths into your build. And so this is one of the helpful things that the build environment does for you. It's you could at some level think of Spack as a big system for shoving compiler wrappers into builds. Spack has the ability to build with external software. We'll talk about this in the config section a bit. You can provide a configuration that looks like this, that says, hey, here's some OpenMPI installations that are on my system. And you can have your build point to that external OpenMPI installation. When you do that, currently we don't consider all of the dependencies under OpenMPI. So it's kind of on you to ensure that those are compatible with the rest of your build. And so what you end up with is a graph that looks like this, where MPI leaks depends on call path, and that depends on OpenMPI over here. But we don't really, Spack doesn't know about what's under OpenMPI because you just told it about the prefix where it's installed. But that's how we support building with external things on your system. You can build layered package repositories. So if you happen to have code that you don't want released to the rest of the world, that you don't want to put in the Spack mainline, you can create your own local repository for package files and your own recipes. You can add it to Spack so that Spack knows about it, and you can build codes that are just in your own package repository. And so you might have some setup like ours where there's a bunch of useful open source in the built-in Spack repository. There are maybe some common organization-wide internal packages, and so that could be in another repository. And then for a particular code team, you can have your own local packages for that code team, and all of these can build on each other. So you can stack these as high as you want. We use mirrors to make it easier to fetch things. So essentially, a mirror is a repository of anything that Spack might need to do a build or a binary installation. And so, Spack actually caches everything it downloads locally. And so if you try to install the same thing again and it already has the tarball, it will try to pull from there. You can cache things on a shared file system. You can make a mirror there. Some sites do, so that their users don't have to download from the internet, or if they're on an air gap, they put a big cache on the shared file system. You can have a cache in an S3 bucket, which we do. Actually, Spack by default depends on mirror.spack.io, and so we mirror all the things that are in the Spack repo, so that you don't have. So if a site goes down, you're not dead in the water because you can't fetch a particular tarball. And then if Spack doesn't find what it's looking for in any of these places, it will go back and look at the original source on the internet, which comes from that package file. So it'll just do a direct download. But there's a lot of places it can look before it has to go to all of the different sites that the software originally came from. All right. So, Greg, do you think it's worth going into the concretizer details now, or should we do that when we get back from break and then continue?
I think we should probably take the break now.
Yeah. So we'll come
A lot
back
of
and finish up
information
core
to assimilate.
concepts. Yeah. So, okay, we're going to leave it here, and we'll come back and finish this section after the break. Let me go over here to share my screen. Yeah. So let's go on break until 10 a.m. Pacific. And yeah, I think I'll just stop the video for now and stop the recording, and then we'll come back after break. So meet us back here at 10. So that's in 30 minutes, and we can take questions in Slack and on in the chat in the meantime. I'm going to stop the recording for now, and we'll pick back up when we get back. Thanks. All right. Okay, welcome back, everybody. We saw a bunch of, we've been through a lot of the core concepts. And the very last thing that I wanted to get across to folks is the Spack concretizer. We talked just a minute ago about how the concretizer converts abstract specs, like this one down here, into concrete specs with everything specified so you can install them. It is actually doing that with a whole lot of information from different places. So the concretizer takes information from package.py files, which come from all the contributors who contribute to Spack, like 7,000 of these, from developers who specify things in places like packages.yaml. You'll learn about this in the config section. From environments, you'll learn about this in the very next section. And all of that, it throws it into one solve that basically converts all of these constraints into a fully constrained graph that can actually be built. This is an NP hard problem, and we use something called answer set programming to handle this. So I'm going to talk a little bit about that just to give you an idea of what's going on under the hood. But to use Spack, you don't need to know anything about answer set programming. You need to know basically at a high level what the concretizer does. So answer set programming is a type of logic programming that it kind of looks like Prolog, if anyone's ever done Prolog. But it's not Turing complete, and it essentially takes a logic description and boils it down to SAT with optimization. And so, essentially the way that we formulate this stuff internally is we take those package files and we translate them into something that looks like this program over here, but with lots more lines. It's like 80 to 100,000 lines for a typical solve. And this tells us everything that we know about the packages, everything that we know about user preferences, and so on. That gets thrown into a solver called Klingo, and Klingo comes out with essentially the solutions, the optimal graphs that we eventually hand you and build. And this has simplified our maintenance of the concretizer a lot. It lets us put a bunch of complicated logic in one place, and it's a complete solver. So essentially, if there is a way to find a spec that satisfies the constraints you gave it, it'll find it. That can be a little slow sometimes, but we are constantly working on improving the performance. In fact, that's something that we're working on right now. And I think the main thing that you need to get from this is how Spack decides which specs to include in the final solution. So you saw in the basic section that sometimes the solver, like if you say Spack install tickle, and you already have dependencies of zlib, or you already have dependencies of tickle installed, that it will prefer to use the things that are already installed. And so essentially, what we're trying to do there is the solver is configured to optimize for not rebuilding things that you've already got installed. If you really want to make your install deterministic, though, you probably don't want it to depend on the state that you have locally. So if you hand a spec to someone else and say, hey, build this, and they run Spack install on that thing, they may get a different result if they have different versions of dependencies installed on their machine. If you don't want that to happen, what you can do is you can use --fresh, which basically says, give me a completely fresh install of this thing. Don't reuse anything that I already have installed. And if you do this fresh install, essentially what's happening is Spack concretizes the whole graph. It takes the graph and it comes up with hashes for everything based on the metadata. And only after it comes up with hashes does it say, hey, is that hash installed or not? And so this used to be the default mode for Spack. We would only concretize things based on the metadata in the graph. We would come up with these hashes and we'd say, hey, is that installed or not? This is really sensitive to small changes. So if you say, if you have a version of libelf installed that is like, one version off from the latest or one like patch version off from the latest, Spack will not make an effort to reuse that if you use fresh. It's going to completely ignore what's already installed and only install based on what it thinks is good based on the current state of the package files. And so, we still have this fresh mode. You can say --fresh. It's kind of like, if you want to upgrade your packages, if you want the latest version of everything, you can use this. But the default mode in Spack is --reuse. And essentially what you need to know with this is reuse takes all the information about everything that's installed that you've already installed with Spack, and it tells the solver about it in advance. And so essentially we're able to give the solver facts like this that says, okay, there's this thing with this hash. It has all of these constraints on it. So you've got an OpenSSL node in there. It's got this version 1.1G. It has all of these other attributes on it. If you use that, you have to essentially adhere to all these constraints. There's some surprisingly simple logic in the solver in ASP that basically says, you can choose an existing hash for any package. We know about all these hashes that we told you about. You can choose one if you want to. So that's basically you're free to pick an installed piece of software. If you choose a hash, you have to impose all those constraints. You have to basically use it the way it was intended. You can't treat it like it was a different version than it actually is. And if you have chosen a hash for something, then it's something that that you're just reusing. If you haven't chosen a hash for something, then we say that you're going to build that thing. And then what the solver does underneath is it minimizes the builds. And so this is how Spack is basically saying, okay, the user has these things. I can plug these ones into the solve. I should really try to minimize the number of things that I rebuild for them so that my install goes fast. And so what that ends up looking like is, if you were to try to install, say, HDF5, and you did a fresh install of it, and you already had a bunch of the dependencies installed, you might get something that looks like this. This is showing the installation status of things. This is showing all of our optimization criteria if you really want to know. But you'll notice that basically none of this was installed. It's saying like, yeah, I'm going to have to rebuild the whole thing. With reuse, what you'll get is this. You'll say Spack solve, and reuse is the default, so you don't really need to say that. You'll get a bunch of pluses over here that say, okay, I found a slightly older version of CMake here that I can reuse. So this is CMake 3.21.1. This is 3.21.4. See, so it said, okay, I'm going to use this older version of CMake because it's good enough. I don't need anything newer for my HDF5 build. Same with these other packages like libxml2, OpenSSH. To install this version of HDF5 that we asked for, 1.10.7, we don't need newer versions of some of these installed dependencies. So you go from building 20 things to building like 4 in this configuration. So the balance is really between building less and having more deterministic builds. Obviously, with Fresh, you're going to build exactly what someone else with the same Spack version as you would see. But with reuse, you're going to get to a solution quicker. So keep that in mind. This is how the dependencies are getting resolved. And you can use Spack Spec to see the results of concretization. So Spack Spec MPI leaks, as you saw before in the basic section, will always show you, what it got, what versions of everything something will resolve to without actually installing it. This just runs the concretizer and gives you the result. All right. So any questions on that before we move on? Okay. The last thing that I'm going to say before we go on to Tammy's section is just a really brief introduction to environments. You learned about abstract and concrete specs. Environments are essentially a way to do that for when you're working with lots of different software packages together. And so you're going to learn that an environment is basically this simple spec.yaml file. It has some specs in it that are the things that you want to install. You can concretize the whole thing and come out with what we call a lock file, which is basically the concrete spec for the whole environment. And you can include interesting configuration and stuff up here to control how these things are built in the environment. And this gets you a nice declarative YAML file that lets you do it in a way that you can say version into repo or work on iteratively. But I'm going to leave the rest to Tammy. So this is just a preview. This is a way for working with, say, a subset of packages together. All right, let's hand it over to Tammy.
All right, can you hear me now? Sharing my
Yep,
screen.
we hear you. I can see your screen. It is a little small. But people
that's
can
what I
make
was
the
going to ask.
WebEx big.
Yeah, it looks like the video's a little weird. Not sure what's going on there.
Oh yeah, you've changed form since the last time I saw you. You're
Okay.
a blob. All right.
All right. So is that good?
I don't know. Is there anyone who can't see that on the WebEx screen? If you cannot see that, then I guess say so or comment it. Someone says better now.
Is that better too?
I think that's pretty good because people can make this full screen if they want to. I think it's pretty visible.
Okay.
Yeah.
All right. So welcome to the environment section of the Spack tutorial. So far we've covered, aside from what Todd has introduced, so far we've covered how to basically manage software in your Spack installation. I tend to refer to it as a Spack instance. The key commands are Spack install to install packages, uninstall to remove them, and Spack find to query them. In this section of the tutorial, got ahead of myself there. In this section of the tutorial, we're going to introduce Spack environments, which Todd kind of already introduced. They allow you to work with independent groups of packages separately and in a reproducible way. In some ways, Spack environments are similar to virtual environments in other systems like Python virtual environments, but they're based around file formats. And as Todd mentioned, the spack.yaml and spack.lock file. That allows them to be versioned, shared, and reused across systems. You can think of Spack environments as basically virtual Spack installations or virtual Spack instances. There are a number of use cases for this, but in this section, we're actually going to introduce the basics of creating and using environments. We'll go through how to expand and add packages, how to configure the environments, change the configuration, and how to build software using the software that you have in your environment. We'll start with the command line interface. In fact, we are going to predominantly use Spack's command line interface, but you can, once you're comfortable, directly edit the spack.yaml file. We'll talk about the difference between Spack managed environments and independent environments, and then finish with a section on reproducible builds that leverage those files. So let's go ahead and start with Spack find. So your mileage may vary in terms of what you see here. But in this case, we should, if you've gone through the basic section of the tutorial, have something along these lines. What we can see here is Spack find gives us kind of a complete list of what Spack has installed or knows about. but it does have multiple versions of, say, HDF5 or Tickle, or I've got a window here that's in my way that I'm sure you cannot see, but not sure how to get rid of. Anyway, there are also multiple versions of zlib. There are times, however, where you might have a task like CI, CD, or you're maybe supporting multiple projects where you want to have just a subset of the software, kind of a clean slate of what's installed, and you only see what is relevant to the task at hand. So what you can do in that case is create and activate an environment. So let's go ahead and Spack env create my project. And what Spack is telling us is that it's created that My Project environment in var Spack environments. That makes it a managed environment. You can actually, it's under your Spack installation. It has a name, and you can use that name to activate it. And Spack also tells us how to activate that environment. But before that, we do that, we can also type Spack env list and see that Spack knows we have My Project. And now we can go ahead and activate it. Now you can use Spack env activate my project, or you can use the alias Spacktivate. I like to use the prompt option, the -p or -- prompt option, and give it the name of, in this case, the name of the environment that we're activating. Scroll up, and we type Spack find now, and what we see is we're in the environment. We also see that the environment name prepended to our prompt. We see no root specs because we haven't actually told Spack what we want in this environment. And we have no installed packages because we haven't installed them at this point. So we can, if you didn't use the prompt, you can type Spack env status to see what environment you're in. Let's go ahead and deactivate it. So we can type Spack env deactivate or use the alias d Spacktivate and type Spack env status and see that we're not in an active environment. Type Spack find, and now we have all of those. We can see everything that Spack has installed in our Spack instance. Do we have any questions at this point? Maybe not. Looks like there's a question there. Installing packages. So let's go ahead and look at, okay, now we have this environment created. How do we start installing packages? Well, you have a couple of choices. You can add them one by one. Again, we're still using the command line at this point, so you can let's go ahead and Spacktivate or Spack env activate my project, and we can Spack install Tickle, try it. But now Spack is not going to allow us to do that. And why? Because we have not told Spack that we want Tickle specifically in that environment. We could type Spack add Tickle. Spack is telling us we can do that. Or if we really did want to install that package, we can use Spack add, Spack install -- add Tickle. So let's go ahead and add Tickle, but actually we're going to add Trilinos. Let's say for the purposes of what we're doing, we want to Spack add Tickle and Trilinos. You can do them individually with Spack add, or you can put them together. Type Spack find now, and we can see the root specs. These are the explicit specs. This is the software that we need in this environment. We need it installed. However, it hasn't actually installed that software at this point. So we can actually install it. We could keep adding packages if we want, or we can, well, I won't do that yet. We can Spack install. What Spack does is we're in an active environment, and Spack is going to install however that environment is defined based on the spack.yaml in this particular case. So Spack's going to go through that dependency resolution process, the concretization process that Todd had talked about. This is going to take a little while. If we actually look at the handout, we can kind of see why. Spack is trying to determine what versions of the dependencies to use and what options are available or defined in the Spack packages. And that's all based on what has been exposed in the package recipes for each of those packages. And it depends on what, how Trilinos's recipe has been built. But we can see that Spack goes through that concretization process and tells us, like I said, the versions it's selected. It tells us the compilers it's used, if it's had to do any patches. And in some cases, for example, we look at OpenMPI, we can see the variants, or build options that have been used to build the software. And then we can also see here that we already, thanks to the first section, had a bunch of packages installed, and we simply needed to install Trilinos. So I'm going to clear that. We type Spack find. And again, we're looking at basically, we want a Tickle and Trilinos installed, and Spack determined that it had to install a total of 40 packages to include Trilinos and Tickle. Okay, now you could have, as I mentioned before, we could Spack install individually, --add them individually, add specs incrementally, but that does affect how the packages are concretized. In general, if you want consistency in terms of the configuration, and you actually want that unify true configuration option or concretization option to be true, you're going to want to add all of the packages up front. It's not always possible, but doing so actually gives you a chance to install all the packages at once. Spack will concretize everything together, and it will try to basically minimize the dependencies, which can reduce the total installation time. You can also use Spack's install level build parallelism. And I encourage you to follow the link if you want to do that, so that you can have multiple processes coordinating the installation of the dependencies for a package. And that can reduce the overall elapsed time to install software. Okay, so now that we've installed some software, we have our environment installed it's important to point out that what Spack gives you is it will pre-populate. When you're in an active environment, it will pre-populate some environment variables for you, specifically path-related environment variables. So if you env and we grep what path equals, we can see the environment variables it's going to set up, most importantly path, and here we can see that because we have a view on our My Project environment, it becomes the first entry in the path environment variable. Now, because we have Tickle installed, we know we have Tickle shell, so we can type which Tickle shell, and again we see that it's in our My Projects view, and as such we can type Tickle shell and actually use that installed software. Hello world, and exit, and there we go. We've been able to use executables that are installed in our environment because we have the environment active. Now, as I said, Spack manages software, and we use environments to manage subsets of that software for some specific purpose, CI, different projects you may support, whatever the case may be. There may be times where decisions are made to maybe uninstall a package that could be used across multiple environments. Well, we need to convince you, I think, that if you uninstall from one environment, you're not going to impact the other environments associated with your Spack instance. So in order to demonstrate that, let's go ahead and create another environment, Spack env create. All right, let me fix this so we can see the commands at the top. And we'll call it My Project 2. And we'll go ahead and Spacktivate My Project 2. And let's add a couple packages. Let's add SCR and Trilinos so that we can use Trilinos as our example. And we'll Spack install. Again, Spack is now going to go through the concretization process, which is that dependency resolution. We can see from the handout, if you will, for this section, that there are a number of dependencies for SCR that Spack has to figure out how to set up to build SCR, as well as wow, a lot, as well as Trilinos, which also has a lot of packages. So do I have any questions at this point, or am I going too fast? No comment? Is anybody paying attention? All right, we're getting close. Slurm?
Don't have
Lip
any
yogurt?
questions
Okay.
At the moment.
Okay, great. And lib yogurt, and now we're done. So then if we type Spack find at this point, we can see that we have SCR and Trilinos. And now for this environment with these packages, we can see Trilinos is installed, we can see SCR is installed, and it actually takes 72 packages to support just those two software packages that matter for our effort. All right, so let's pretend that we've come along and we've decided, oh, my project too, I don't want Trilinos anymore in that software. For whatever reason, I don't want to use that. I don't want to associate with my environment. So you can Spack uninstall. We do minus yes, minus Y for yes, telling it to automatically respond yes to the prompts. And we can go, well, let me uninstall it. Well, Spack's not going to do that for us because the my project environment depends on it. So Spack also tells us there are a couple of things we could do. We can remove it from our environment. We can force it to be uninstalled. I'm going to go ahead at this point. What we want to do is let's go ahead and use another Spack command and say type Spack remove Trilinos. And if we type Spack find, we can see that in fact Trilinos is no longer a root spec in our environment. If we wanted to add Trilinos back, say we did that by accidentally, we could add it back before it's installed as part of the environment, although I still see it there, but we'll pretend we're not seeing that. Let's go ahead and Spacktivate my project. And Spack find, just to convince ourselves that Trilinos has not been removed from our first project. So it is still a root spec in our first project as well. All right, and it's important to note that, as I said before, Spack wouldn't uninstall Trilinos if it is needed by any of the environments that Spack manages, or it's a dependency of any packages that Spack has installed, at least not unless you force it. All right, so far we've been using that spack.yaml file. Right, it's an environment, it's more than just a list of root specs though. We can actually change the configuration settings. At this point, for example, we have been, well, I'm getting ahead of myself. Let's go ahead and look at what that spack.yaml file is. So we spack config edit, where my project is our active environment, and we can see we can tell this is our spack.yaml file. We can see the root specs that we had and the default. So the root specs, those are the packages, explicit packages that we've told Spack, these matter to this effort. We see that view is true, so we get that prefix set up where the prefix has symlinks back to the Spack's actual installations. We have concretizer unify set to true by default. This controls how the concretization process works. It is true by default, and that basically means that all of the specs in the package at the time it is concretized are concretized together. And one of the side effects is that there will be only one version of each package in that environment. Other options are false. If it's false, then each Spack is concretized independently, which may mean that there are multiple versions of the same package in the environment. And then there's when possible, which is kind of an option in between, where Spack will try. I saw that. Spack will try to concretize as many packages as it can, and if it can't concretize all of them, it won't fail. So the view actually, the view option is either true or false, and if it's true, then Spack will create basically it has a directory associated with the environment in that. Sorry, go ahead.
So Tammy, a couple questions come up, one of which is asking, can you explain what a view is again? And then another, when you get through talking about the views, can you go back and explain the interaction between multiple environments when you're removing a spec from one of them, or removing a spec that's in both from one of them again?
Okay. So the view is a directory, and the view, when it's true, contains symbolic links back to where Spack manages the software that's been installed with Spack. That allows different environments to basically share the installations of packages. You have it installed once, and the view, like I said, it has links back to where that software is actually installed. Am I answering your question, or should I explain that more? Okay.
Yes. Okay.
All right. And then the other question was if you remove, so environments, again, I kind of touched on that. If you have multiple environments, if you have multiple environments that are basically pointing back to this or sharing an installation of a package, right, of a spec. If you have multiple environments that are basically using the same installation, just because you remove from one doesn't mean you remove from the other, because the installation, Spack actually keeps that installed software in an installation prefix, and then those views basically symlink to the install prefixes that are relevant to the environment. Is that the kind of detail that you wanted, or was there something else? So when you actually remove one of these, you're removing that, when you have a view, you're removing the symbolic link, I believe, from that points to the actual installation. And then Spack probably, I'm sure, does some more extra things to determine whether it's suitable to remove the package overall. Okay, so I see it. If view is false, we don't get. All right. That's distracting. Did we answer the questions between Greg and I?
Sean, did that answer your question about a spec remaining in one environment versus not in another, and whether it's a root spec or not?
Yeah, I think it mainly is just that the software, even though it's not a root spec, but it still exists in that environment.
Oh, yeah. So you need to so after you make a change to the roots, you need to concretize again before that will be reflected in the specs listed as installed.
And will that actually remove the, does that software take up any space in that environment, or since it exists across all environments, it'll just take up the same amount of space?
It'll take out the same amount of space. You will get back a few inodes because you'll remove the symlinks from your view back to it.
Okay, that's the question then. Thank you.
Okay. So is it okay to move along?
Yeah, I think that's all the questions that we had.
All right. Okay, so now there could be reasons, say your project has come along and decided, we don't want to use OpenMPI, which is the Spack default implementation of the MPI virtual package, or message passing interface. MPI is a virtual package. There are multiple implementations of MPI, so there are multiple packages that can actually provide that MPI interface. Let's suppose that in our project we actually want to change what we're using. We don't want OpenMPI anymore. We want MPitch. So we can use this Spack config edit to actually modify or add configuration to our spack.yaml file. You will need your editor environment variable set to your preferred text editor. And what we can do here, and you'll learn more in the configuration section, is that we can say, tell Spack as part of the environment's configuration, we can say for packages, this MPI package, which happens to be a virtual package, right, that we require it now to be, in this case, we're just going to require it to be MPitch. It actually takes a list, but we're going to say we're just going to require it to be MPitch. So I can modify this. I'm going to copy and paste just to save everyone time. And then you can save that. And so this is, again, this is one example. We're saying that we basically want Spack, at least from now on, to require that the MPI implementation be MPitch. Now, because we've done this, we probably want to reconcretize the environment. If we've said, no more open MPI, everything needs to be MPitch, then we definitely have to reconcretize. We have software installed. We have that software installed, as we can see here, with OpenMPI. There's no MPitch in our environment. It needs to be MPitch. So what we can do here is we need to Spack concretize --force or -f, and Spack will go through that whole dependency resolution process, options, dependencies, but it's actually going to say, it recognizes now that we've said the MPI implementation shall be MPitch. And we can see here that it's going to take a while because these are large packages. Trilinos will go through the process, and we can see in the basically in the tutorial handout that MPitch will be the MPI implementation. It was OpenMPI, and to convince yourself, if you don't recall, you can scroll up and see that it in fact was OpenMPI. So we have MPitch here, and Spack updated our view. All right, so let's see. So now all of our specs are concrete and they're ready to be installed with MPitch as the implementation. There can be other situations in which you need to reconcretize things. Suppose, for example, you had been adding specs to your environment. You're adding new software and you're installing it. You're not doing it all at once. You're kind of doing the incremental approach. But you've made a similar decision. You're adding some new package, perhaps that depends or can only use an older version of software you already have installed. So we have an example here of that kind of scenario, where clear. So let's Spacktivate --temp, and I need to make sure I'm using my option. And we can see that if we Spack install --add Python, our first package in this temporary environment, Spack will basically take the latest version of Python. And this will take a little while. And then suppose we come along as that's working. So we have our environment with just Python, and it is the latest. Now let's say we come along and we say, oh, I want to use PyNumPy at 120, at 1.20. So if I type Spack install and I add PyNumPy at 120, I'm going to redirect it and just tail the bottom part so you don't have to see all the other information. But basically, Spack is not going to be happy with this. The concretizer dependency resolution process is not going to be happy with it because there's a conflict. Remember, by default, the concretizer unify option is true, which means that all of the specs, Spack is trying to resolve the dependencies for all of them at the same time. So this is a problem because apparently PyNumPy can't take the latest Python version. So we have a couple of options that Spack is telling us about. We can force concretization as one option, or we could change that configuration that we had from true to when possible or false. So if we go ahead and add, so we want to Spack add because if we do Spack find, we'll see that all we still have is this Python, right? Spack wasn't able to be successful. So let's add that NumPy at 1.20 and type Spack find, and we see it has it, but it's not installed yet. So we can Spack concretize -f or -- force, and Spack will again go through the dependency resolution for both packages because remember unify is still true, and then it will update. How am I doing on time?
You're doing fine on time.
Okay, great.
It's
So we
it's better to take time out of the config section than out of this one anyway.
okay, so we can see now our Python has changed to 398 because of PyNumPy, and we can see that PyNumPy is dependent on Python 398. So now that environment is consistent with our concretization choice. So you could then install the software, but let's go ahead and proceed with how to actually use another example of using our environment. And in this case, we're going to actually build some software. So I'm going to Spacktivate or Spack env activate my project 2. And I can type Spack env status, env status, but I already used the prompt, so I already know where I'm at. If I type which MPICC, I can see that I'm getting the compiler from my project 2 environment. And as we looked at before, you can actually see path-related environments. If you look at the environment and corrupt for path equals. All right, so let's go ahead and do your kind of standard hello world MPI example. MPI hello, bring that up in your favorite text editor. And I'm going to just copy and paste this. So this is your standard MPI hello world, but with a slight twist. And the twist is that we're going to include zlib, which if we look, zlib is actually also installed in this environment. And we'll have the first process actually output the zlib version. So let's save that off. And MPICC, MPI hello. Now, Spack did set the path, a bunch of path environment variables, but it didn't set includes or anything like that. So we can use the handy Spack location command. So Spack location -i for installed. So we're telling Spack we want the prefix for the installed zlib. So the installed zlib that we know of in this environment, and we want to use the include subdirectory of that. Excuse me. All right, now we can actually run this. So we'll use MPI run, give it 4 processes. And there we go. We get our hello world from each of the 4 ranks, and the first rank outputs the version of zlib. Now, since I didn't keep on my terminal, I did not show what we have. I can do a Spack find zlib at this point, and we can see that the zlib that's installed is actually 1213, so they match. Okay, so now we've covered, how to create environments, how to install software, remove software from them, how to use the binaries that are installed with them, and how to build software with them. Let's look at those environment files, how we actually define our environment. Again, Spack has our environment is kind of a virtual Spack instance or installation. We use these spack.yamls and spack.lock files to define that environment. The spack.yaml is the abstract specs. That's just those package names and any options. You can definitely use, any of the sigils, however you normally, as we saw before, however you would define a spec, you can use that here. And that configuration, as we've already seen, the spack.lock file is generated by Spack when you successfully concretize an environment. And these files, we've taken this file-based approach so that developers and administrators can reuse those environments in a reproducible way. You can, as I said before, you can version them, you can share them with other people. You can build the same software either approximately with that spack.yaml or exactly with the spack.lock. But before we go more into that, let's look at that managed versus independent environment. So far, what we've done is used a managed environment. We've used Spack env create with a name, and Spack places those environments under our Spack environments subdirectory using the name as the subdirectory of that path. Independent environments can live anywhere else, any other directory. Spack does provide a command, Spack env create -d for the directory, and then you provide that directory. And then the spack.yaml file and once concretized, the spack.lock will reside under that directory. You access those independent environments with the path. So let's look a little bit more about a couple of capabilities we have in terms of accessing our managed environments before we proceed with an example of an independent environment. So Spack, we can Spack cd -e or --env, I believe it is, my project, pwd, and we can see that Spack cd has moved us into the my project subdirectory within our Spack installation. We can ls and we can see the spack.lock and the spack.yaml files. If we type Spack env list, we can see that we have 2 of these managed environments, and because my project 2 is highlighted, we know that that's the active one. I also get it from prompt, but I like that. All right, so let's look at cat of spack.yaml. Let's look at that spack.yaml file. And this is basically what we had before. Remember, we started with Tickle and Trilinos in my project, and we added packages, that configuration, require impitch as the MPI implementation. This is actually the same output if we did Spack -e and it's my project, config get, they're the same thing. So 2 ways of accessing it. We can go into the directory and look at the spack.yaml directly, or we can use the Spack config edit command. All right. Any questions? I see somebody typing. Should I wait? What am I doing? What do you mean a global environment? So David, did you want to speak up?
Sure. A little while ago, I installed a test Spack installation with like 0.18 to do some testing, and then .19 came up, and I wanted to transfer everything over. I made some mistakes and fumbles, but I wanted to, get all the packages, versions and dependencies and all that exactly the same in the new like .19 environment. And I was told either on the mailing list or in Spack that to do this, it'd be best to have to do it like in an environment. So I was wondering, should the default install that's available globally be in some kind of environment to make certain operations easier, to transfer to, from your laptop to your home DIR on a HPC cluster or something else. So should there be like a default environment for administrators or users?
I think what you want is really more of a command to spin up something ad hoc, because Spack environments cannot nest. And so you don't want the default to be in an environment and then anything that you install in another environment doesn't show up there, and now you're trying to recreate the whole state of your Spack tree. But you need to kind of collect all of the environments you've ever used. We don't have any particular plans for something like this, but it's not infeasible to do something where you could say list a bunch of specs, Spack, kind of pipe the output of Spack find into the creation of an environment.
Yeah, that's what I ended up doing because I accidentally used a newer architecture of microarchitecture of CPU, and some of the older machines couldn't use like Python. For example, it's segfault because of invalid CPU instructions. So I did end up creating a command line utility that I extracted all the various options and rebuilding under the correct microarchitecture. It was just a matter of it was suggested that if you could put it in a environment, it's a lot easier to export. If you compile something on like your laptop and then you want to recreate it in the HPC environment that a user logs in more regularly, it's easy to do that using environments. Yeah. So I was wondering, from a sysadmin point of view, would there be any advantage of having a global default environment?
When I am using Spack to administer what goes onto a cluster, I do it all from a single environment. So in that sense, right, it's per use case, not per Spack instance. But yes, the environment is definitely the best way to do that. But there's some technical challenges to having a global environment.
Okay.
Okay, should we go ahead and move on? Any other questions? All right, so I'm going to assume that's a no. So we've looked at those managed environments that you can access by name. Let's look at how you can go about creating an independent environment. Let's go ahead and cd to the root directory so we can keep things clean. Make dir code, cd into code, and spack env create -d. So we're just telling you to use a directory, and for simplicity, I'll just say dot for the current directory. We can see that the environment is home is basically the path to this directory, right? And that we would activate it with that path. And if we ls, we can see that Spack created a spack.yaml file for us, and it's actually a skeleton. So if we cat the spack.yaml, we'll see that the specs is this open and close square brackets, which means that specs is expected to be a list, a YAML list, and we can see the view and concretizer unify option defaults. We can also type spack env list and see that this environment is not showing up as a managed environment, right? Spack env list only shows those environments that are managed In other words, only those that live in that var Spack environment subdirectory. Okay, then, oh, and we can also see that my project is highlighted and therefore it is still the active environment. You can bring up your spack.yaml in your favorite text editor, and let's add a couple packages to it. Let's go ahead and add Trilinos, and let's add OpenMPI. Keep the defaults the same, save that off, and go ahead and activate it. By again giving it the path as instead of a name. We can see that the prompt option actually just uses that the root node of the path or the directory that we're currently in. We can, because we've added all the packages that we want in it, type spack install. This again will go through that dependency resolution process for the two packages, OpenMPI and Trilinos. And so it will take a couple minutes.
I jump in with a question real quick, Tammy.
Sure.
So, just to clarify, this is an independent environment, meaning the environment files are not inside of the Spack installation, but the code that will be installed still will be, correct?
Yes.
Because we don't have install tree set. I think.
Well, yeah. So I could have set the install tree someplace else, but I believe that install tree setting. Oh, I can't remember. Do we now support install tree setting on the spack.yaml file? I think we might.
Yeah, you can set it somewhere else if you, but you don't. If you set it somewhere else, then you have to duplicate all of the work of installing the dependencies. Whereas if you have all of your environments using the same install tree, you get the dependencies that are overlap with your other environments for free.
Right. Okay. Thanks.
Okay, so we went through the process. All the packages are already installed. Spack was able to make that distinction. Or to basically concretize, we see OpenMPI. We can also see that Trilinos concretized with OpenMPI. So there we go. We got that stuff. Now, if say we wanted to add a package, just because we use the editor, text editor for creating, or I guess adding the initial packages to the spack.yaml doesn't mean we can't continue to use the Spack command line. So we could say Spack add hdf5 at 5.5.1. And if we cat our spack.yaml, we can see that Spack added it to the end of the list of specs. We can also remove that, Spack remove hdf5, because there isn't any conflict. We can just remove it by the name only. And if we cat that, we can see Spack has now removed it from the list. So again, we can either edit directly or use the Spack add and remove commands on that spack.yaml file. Now, as I said before, when you successfully concretize your environment, Spack will create this spack.lock file. And we can see we have one here. Now sorry, let me go ahead and ls those again. The spack.lock file is, although it is kind of human readable, it's not as readable as the spack.yaml. Remember, spack.yaml is, I need these specs, these packages, maybe these options, or these packages and versions and options, whatever the case may be, and I want to configure it a certain way. So that's kind of an abstract representation, right? The spack.lock is that fully concretized state. It has the commits, the Spack version, the Spack commit, it has our root specs with the hashes, and it has all of the specs, as all the concrete specs, the names, the versions, the architecture, the options, etc. So it is less human readable. If we actually look, we could do a word count, a line count rather, on the spack.lock file. In this particular case, at this point, it's actually 1,895 lines. So there's a lot more verbose than our spack.yaml file was. And we can look at the top 30 lines of spack.lock. And we can see, as I said, there's some metadata information about our version and spec version for spec.lock and our commits version, those root specs, those explicit specs that we need in our environment, that we want installed in our environment, and then that whole everything that got concretized. So you're welcome to look at what that looks like in detail. The important thing from a reproducibility standpoint is that you can use these files to actually create a new environment or create an environment somewhere else. We can use the spack.yaml file. Again, it's abstract, so it's an approximate reproduction of the environment. And I say approximate because all we've said is I want these packages installed, maybe with these options, and I want this configuration. But I haven't said on what platform, what specific versions. It doesn't have all that dependency resolution information associated with it, but we can still use it. We can do spack env create, and let's call it abstract spack.yaml. And Spack has told us it is now, we've created a managed environment called abstract, right? Abstract under var Spack environments, and we've been told how we can activate it. So if we activate abstract, because we can use, it's managed, so we can use just the name, and Spack find, we can see we have those two specs, the OpenMPI and Trilinos, that we put in that independent code environment, but we don't have anything installed in that environment at this point, right? But if we use the spack.lock file to create a new environment, we can type spack env create using the spack.lock file. Then we get another managed environment called create. We can activate it, right? So we can activate concrete and Spack find. And because that file has all of that dependency resolution information already available in it, Spack can take advantage of that and because we're in the actual installations are managed by Spack. Spack has set up the view for us to point, all those symlinks are pointing to the actual installations in our Spack instance. So we can reproduce that build, quote unquote, exactly, but that does, at this point, we are constrained to reproduce that build on the same type of machine. And you can look at the spack.log file and maybe understand a little bit more as to why that's the case. All right, so that's all we really have for the environment section. We do have pointers at the end for more information, like how to set up and build environments. So the reference docs, the configuration tutorial coming up next, the stacks tutorial, I believe Greg mentioned tomorrow. There's a link to the installed level build parallelism if you don't want to search at the top of the, where we referenced it before, and ways you can use environments. So the developer workflows, Spack CI, you can generate container images, and again, the stacks. So thank you very much for your time. I don't know if we have time for more questions or if you want to have more questions, but we are done with this section. So thank you very much.
And given we're a little bit over time now, let's take questions in the chat. I see one's already coming up. So Tammy, you can respond in Slack, and I'll keep moving forward with the configuration section of the tutorial.
Okay, let me stop sharing.
All right, so we're going to talk about configuring Spack, and even if we had all the time we would normally allot for this. This is only going to be a brief overview of all the things you can configure in Spack. So first thing we're going to do is we're going to add some configuration from the command line. We're going to say spack config add concretizer, so that's the section of the config that we're dealing with. Reuse is the value, and we're going, or the key, and we're going to set it to false. And we talked about reuse in the concept section. We're setting this to false now so that it's easier for us to see what the preferences are, and so that we'll see things picked up more easily by the concretizer. So there are a lot of places we can specify configuration in Spack. There are configs that come in from the command line. Those are the highest priority. They're not written to a directory ever. They're just commands that alter configuration. You can have configuration in your environment. That's the next highest priority. You can specify a directory of configuration as part of the Spack command, which takes on a higher priority than the user configuration in your home directory, the configuration which is unfortunately labeled site, but is the instance configuration in the Spack tree. We've kept the name because it's been that name for a long time. There's also system configuration that if you're a sysadmin, say, and there's configuration that should apply to all users on your system, you can set that in /etc/spack. And then there's the defaults, which are also from the Spack tree, etc spack defaults. And you should treat these as read-only. There's never a reason that you need to update the config in the defaults, but we provide it so you can see what the configs look like and what the default values in the code are in a more intelligible way. So there are also platform-specific scopes. So not for environments, but for the home directory, for the site and system config, and for the defaults, there are subdirectories for each of the platforms, the major platforms being Linux, Darwin for Mac OS, Windows, and Cray for older Cray machines that we couldn't support directly as Linux. Configuration in Spack is all in YAML files, and the YAML format is almost completely vanilla YAML with one slight addition, and that addition is the double colon. So when we're combining the configurations from all of these scopes, we read the lowest priority scopes first, and then we merge in the configuration from the higher priority scopes. If we encounter something, a key that is set off with this double colon, we drop all of the information from the previous scopes and just use what's coming from that scope and later. So as an example, here is a snippet of Spack compiler config that says, I have this compiler, it's GCC 11.3.0, here are the paths to it, here's some metadata, and ignore any previously defined compilers. So this can be very useful in an environment or something of the sort to say, we're going to use this GCC in this environment, ignore what I have configured on my system. Configuration in a Spack environment is always set off under a top level or there's the Spack key at the top of the environment, and then the next level key is the name of the configuration section. The config outside of a Spack environment is exactly the same, except that you omit this top level Spack key, and so you'll see the name of the section appear at the top of the file. And as we go through, we'll do half of this section in an environment and half of this section outside of an environment, and that will help us kind of see what's going on. So first, we're going to talk a bit about compiler config. So in the basics section with Resharda, you saw how you can add and remove compilers, but behind that is a YAML file storing which compilers are available. So if we do a Spack compilers command, which is the same as Spack compiler list, we can see we've got these 3 compilers. If we do a Spack config get compilers, we'll see the same compilers in YAML format. And if we do a Spack config blame compilers, we'll see that all of these are defined in our home directory in the Linux platform. So most of the config sections by default go in the non-platform specific scope, but compilers tend to be platform specific, so we put them by default in the platform specific scope. If we run Spack config edit compilers, I'm going to get a VI terminal, so that's not going to work. I'm going to set my editor so that you don't have to watch me flail around in Vim. And I will run Spack config edit compilers again. All right. So here's our compilers config. And we see we've got Clang, GCC, GCC. That's what we would expect. And so now we're going to add a new compiler. And we're going to do this manually. So I've just copied my Clang config. I'm going to rename this compiler to be Clang at 14.0.0 G4tran. And we're going to configure this to be Clang for C and C++, but we're going to use G4tran for Fortran. And this is a pretty common config for Clang because Flang hasn't really taken off yet. So when we look at this spec here, it's worth mentioning the name of this compiler spec has to be one of the compilers that Spack knows about. The version can be anything that we want. It's usually best to start with the number, even if you're going to add to it, because that makes it easier for Spack to auto-detect which flags to use for it, but then you can append whatever information you want. So we're going to make sure this compiler works. We're going to say Spack install -- no cache. And we're going to say zlib %clang at 14.0.0 G4tran. And so the no cache option means that we won't use any available binaries to satisfy this. And it's installed. And that's not a great test for a Fortran compiler, of course, because zlib is in C. So we're going to Spack install -- reuse cmake %gcc at 11.3.0. So this is just getting a cmake available that we can then use to build something that uses cmake. It may well already be installed for some of us. And then we're going to Spack install -- no cache JSON Fortran. We're going to build with Clang at 14.0.0 -G4tran. And we're going to build with the cmake that we just built, which was EQFR, which had the hash E. No, that was the zlib. OFS was the hash for cmake. I will mention that there's an error. There was a persistent error in this script that it says Clang at 7 everywhere that it should say Clang at 14. We will fix that going forward, but if that is messing you up, you can Spack config edit compilers again and change it to 14. Okay. So we've now shown that this compiler works for both C and Fortran. Now we're going to make one more change to it. We're going to Spack config edit compilers. It would help if I could spell. And we're going to modify the flags. We're going to say, for the C preprocessor flags, which means it gets applied to all of the languages, we're going to add -G. So we're going to create, every time we use this compiler, not only are we mixing Clang and G-Fortran, but we're going to create debug symbols for all of our builds. And this is a good opportunity if you put Clang at 7 the first time to correct it to Clang at 14. So now we don't need to build anything more. But if we run Spack spec, JSON Fortran, %clang at 14.0.0-G Fortran, which is our new compiler, we're going to see that this compiler flag is going to be added to every node in the DAG, and more specifically is added to every node that happens to be using this compiler. So we'll see everything's using that compiler. They all get it. If we build with the CMake from earlier, which was built with GCC, we'll see that it's not applied to those nodes, obviously. While that's running, we can talk about some of the other fields on the compiler specification that we haven't talked about. The target specifies the target family. That's x86 64, AArch64, PPC64LE, PPC64. Could also be for some of the 32-bit architectures, but those are much less common these days. The modules field allows you to specify modules that will be loaded anytime the compiler is to be run. This was originally implemented because of older Cray systems that required modules to be able to use the compilers. That's not true anymore, but there are sites where the compilers are configured in such a way that if the module isn't loaded, they can't find their runtime libraries, or they can't find the licenses they need for Intel compilers, say. And in those cases, you can have the compiler load a module. You can also set arbitrary environment variables. You can set, you can unset, you can prepend paths, you can append paths, things like that. And then lastly, you can add directories to be rpathed as part of any invocation of that compiler. And that will set a library path and an rpath for that directory. And that's another way of working around compilers that don't, by default, know how to find all of their runtime libraries. All right. So now let's talk about package preferences. So we're going to switch which section of the config we're talking about, and we can say Spack config -- scope is defaults, edit packages. Now we're going to treat this as read-only, but we're just going to use this to look at this config. We can see here's the compiler preferences. Within each one, it prefers the newest version first. Here are all of the provider preferences for our virtual packages. And you can see in the basics section earlier, we talked about the MPI preference and it's preferring OpenMPI over MPitch. It's preferring both of those over anything else. This does not prevent you from using a different version or a different implementation of MPI. It just doesn't set any preferences among the other implementations. So, exiting out of this, if we do Spack spec HDF5, we will see it's going to use GCC and it's going to use OpenMPI. And this is what we saw earlier on when we installed HDF5 in the basics section. So the next thing we're going to do is we're going to create an environment, and we're going to do the rest of our configuration for this section in that environment. So Spack env create config-env, Spack env activate. I'm going to add -p for a prompt config-env. And when you're in an environment, Spack config edit without any section will just open the environment. And we will add to this a packages section. We're going to configure a compiler preference for Clang. We could specify the rest of the order if we want to, but we don't need to. We're going to specify providers. And we're going to switch the order of MPitch and OpenMPI here. So because of the ordering of the config scopes that we talked about earlier, this is going to be the highest level config. We're going to see this borne out when we run Spack spec HDF5 again. So I made some sort of error here.
Package is indented 1 character, maybe?
Yes. It's not a configuration tutorial without me messing up the YAML format at some point. So we'll run Spack spec HDF5, and we'll see that these preferences will be taken. So we'll see %clang throughout. In fact, it's going to use our new clang that we configured because 14.0.0-G Fortran is just a smidgen higher as Spack considers version numbers than 14.0.0. So we're using our fancy new compiler with Fortran support, which is good because we're also using MPitch, and MPitch requires Fortran to build. And you can see we're also still getting our compiler flags. So we can also specify variant preferences. So we're going to Spack config edit again. And for HDF5, we're going to require ~MPI. So there are multiple ways to set preferences in Spack. I'll run Spack spec HDF5 again and talk about it while this is happening. There are multiple ways to set preferences in Spack. One is preferred, and the other is to, so you could say variants ~MPI, and that would be a preference, and Spack could choose to ignore it if there was some other priority that was easier to satisfy if Spack ignored it. If you set require, it's a requirement, Spack can't ignore it. And in this case, you see we're getting a serial version or spec for HDF5. In general, anything that we can set for all, we can set for an individual package. we can also configure external packages. So if we already have Perl on the system, we can say there's an external for Perl. It's, I happen to know, version 5.26.1, and it's built with the system compiler for the system, which is 11.3.0. And there it is. And we don't have to specify everything we could possibly know about Perl. It's great if we can, but if anything that we don't specify, Spack will assume is compatible with what we're trying to get. So you only need to specify it if it's relevant for your ability to build against it. And now if we run Spack HDF5, we'll see a whole chunk of this will go away. Todd mentioned earlier that we trim the dependencies of externals. And here it is. So I see a question about the prefix. The prefix for Perl is /user because the prefix that you need to specify for Spack is the Unix prefix into which the package was installed. So generally, if it has an executable, that will be the directory containing the bin directory containing the executable. The libraries for Perl are in user lib, the bin is in user bin.
And Greg, there was another question about telling the compiler that, or telling the system that the compiler doesn't support Fortran and therefore not support packages built with that compiler. I know we can set it to none. Does the concretizer actually pay attention?
No, the concretizer does not currently pay attention to that. We're working on revamping the compiler model very substantially in ways that will make that kind of irrelevant going forward. All right, so we see that we used our Perl, but we didn't use our preferred compiler anymore. Because Spack said, okay, I can use an external, I can limit the number of builds that you're doing, but that's built with GCC. That means you probably want everything built with GCC. So if we want to build with Clang, we have to specify now, okay, but we still actually want Clang. Right, and this is because, like I said, lots of things in the packages section are preferences, not requirements. We set a preference for Clang, but unifying the compilers across a DAG is a higher priority. And what we see when we go to use Clang is it says, okay, well, that's a higher priority than using keeping the compilers the same is a higher priority than using the external, and so it ignores our external Perl. So what we really want in this case is we want to say, no, you have to use this Perl. If I want something else built with Clang that depends on Perl, you still have to use this Perl. So we're going to say buildable false. Spack is not allowed to build any other Perl besides the external one that we've listed here. And now when we do HDF5% Clang, we will get HDF5 built with Clang, but Perl from our external that we happen to know was built with GCC. There is not any verification that there's a valid Perl in that directory. You have to configure it. You can also use Spack external find, which for a lot of packages can find these externals and automatically configure them for you. So we're going to we're going to do the same thing with MPI, but things get a little more complicated with virtual dependencies. So I'm actually going to do a Spack external find mpitch. Okay, so there's no mpitch in our path right now, so it didn't find an external.
So, Greg, there's
Okay.
also a question about whether there's some sort of verification or check that a valid Perl is actually found in the location that you have listed in the config.
I thought I had just answered that. No, there is no validation. So we're going to do a Spack config edit. So let's say we're doing this for mpitch. We're going to configure externals. We're going to say, okay, it's mpitch at 3.3, built with GCC at 11.3.0. Prefix and /user. And now if we just...
You said 3.3, but you typed 2.2. Was that intentional?
No, thank you. So if we just set buildable false for mpitch here, it will say, okay, that's fine. I'll go build OpenMPI. So that's not what we want. For virtuals, you have to specify, or you generally want to specify buildable false for the entire virtual. So we'll say MPI buildable false. And now, if we spec HDF5% clang, we will see, actually we'll see a serial version because we never got rid of the requirement to build it serial. So I'm going to kill that real quick. Spack config edit. We're going to remove that requirement because we want to see what MPI we're going to use. And we'll see that it uses both our external Perl and our external mpitch. So the last thing I'm going to talk about with the packages config is that you can also use it to specify group or world readable, writable permissions on the things that you install. By default, everything that you install is user writable, world readable. Although, of course, if you install it into a directory that's not world readable, it won't be, it won't be world readable through that path. But you can specify a group per package or for everything. And similarly, you can specify the read and write permissions to be user, group, or world. So we are going to Spack env deactivate to get rid of all the configuration that we just did. And then we are also going to Spack config remove concretizer reuse, right? Because we added it at the beginning and we're not going to want it for later sections of the tutorial. And if we do a Spack config blame concretizer, oh, yeah. See, now it's set to true. I just misread it the first time. It was already set to true. All right. So there is also a high-level config in Spack, which is the config section. And we've already gotten a couple of questions related to it, right? You can see the install tree is here. This includes a root and a projection. We'll talk about projections more when we talk about complex views tomorrow, but it's basically the naming scheme for packages. We've talked some in the Slack channel about the build stage. This is where the stuff is built. Tempter, because that's typically fastest. Where our tests run, where do we cache downloaded sources, where do we build internal caches, etc., etc. So feel free to look through some of these other configs. I'm not going to talk about it in a huge amount of detail. But all of this is available. You can use it to set the maximum number of cores that will be used to run make and things like that. And since we're over time, we will conclude there. That's the end of the config section. If you followed the instructions that I've done so far, your VM will be left in a good state for the sections that we are doing tomorrow, so you won't have these configs interfering with the configs or with the sections we'll do tomorrow. We're going to leave the VMs up overnight, so you're not going to have to get a new login in the morning. You can use the same login tomorrow. That also means that if you want to play around with some of this, go back over sections. If you felt like you didn't understand it fully, feel free to do that. The VMs are available to do that overnight. We will start again at 8 a.m. Pacific time tomorrow with I believe we'll do the stacks section first, but I could be incorrect about that. I think we'll do stacks and then writing our own packages and then scripting. All right, and with that, I will stop sharing my screen and I'll turn off the recording and we will reconvene tomorrow.
And feel free to ask questions in Slack. We'll be around.